going to do our last topic of deflection, which is Castigliano theorems. Okay. Actually, it's the theorem number 2, which is related to deflections. Theorem number 1 is just for understanding. So, mostly today I'll try to cover the background, okay, the conceptual background behind the Castigliano theorems, and we'll do problems then hopefully in the next class. Okay? So Castigliano theorem. Castigliano, he was a structure engineer and an Italian rail engineer, and he came up with 2 theorems. These are again very important theorems if someone is looking into advanced mechanics. These like finite element analysis or advanced structure mechanics. Okay, if someone is thinking of taking that in the post-graduation, then these theorems, they are very important for that, for understanding of all the mechanics, theory of elasticity, plasticity, and all that stuff. And based on that, you have got finite element analysis developed. Finite element analysis, simple finite element analysis like or structure analysis programs like ETABS, SAP 2000. That is involving just a portion of finite element analysis, and some advanced finite element analysis such as abacus, ANSYS. May I please ask, okay, to switch off either your phone or make it slower, okay? I don't want that thing. Okay, make it either slow, okay? Just mute the ringtones. So the theorems, these theorems, they are very important from the advanced structure mechanics point of view. As I said, that finite element analysis softwares, they are also divided into 2 parts. One is normal finite element analysis packages, like we have structure analysis packages, SAP 2000, ETABS. These are not very advanced. Okay, they are using very simple elements to model structures. Okay, these, and then you have advanced structural finite element analysis such as abacus, ANSYS, and those softwares, they are involving very advanced elements. Finite element analysis is all about elements. What sort of discretization you do, what sort of elements you take, but that is advanced topic. All these softwares, they are based, the mechanics of these software is based on these theorems, Castigliano theorems, and the one which we did previously, that was virtual work equations. So that plays very important role over there. Today we do 2 theorems. We'll discuss 2 theorems. One is theorem, the first one is theorem 1. What this is involving is there are certain terminologies which we must understand. First thing is elastic structure. What is an elastic structure? An elastic structure is a structure, for example, if you draw a P delta curve for that structure, for any structure, you can have a bar, you can have a beam, you can have a plate, whatever structure you consider. If you start like in your PRC, you have tested cylinders. So that is also a structure, isn't it? That's a small structure. So you would have, if you are testing cubes or a cylinder, okay, simple in a universal testing machine. That is also a simple structure, a stub, okay, and you get a stress strain curve out of that. So, if you draw the stress strain curve or the load and deflection curve, okay, this can be a load and extension curve, and that comes out to be straight. Okay, that is an elastic, linear elastic structure. But one thing is important in the linear elastic structure. If your loading path and unloading path, that is the same. So in other words, you have your tube or a cylinder or any structure, a bar or anything in a UTM, and you apply load on it. It goes to a certain point, then you stop the application of that load. It follows the same path and come back to its original position. That is a linear elastic structure. Beside linear, we can have a non-linear elastic structure, which will be a curve. It's not a straight line. But again, in the non-linear elastic structure, we have the same problem. We have the loading path and the unloading path the same. Okay, that is an important part of important characteristic of a elastic structure. Okay, if you have a non-elastic structure or a plastic structure or a sometimes called elastoplastic structure, okay, what happens in that? In that you have a, in that you can have a straight line or a curved line, okay? You can have a straight or a curved line when you are loading it, but at the time of unloading, what happens? You have a residual deformation. Okay? So imagine you have got a thin wire and you extend it. Okay? And it reaches there reaches a point where beyond a certain extension, that extension remains permanent. Okay, it doesn't come back like a rubber band. In the case of rubber band, the extension comes back. But you can have a steel wire where you extend it to an extent that it doesn't come back, or it slightly comes back, and then there is a residual displacement in there. Okay, in other words, the final displacement is the final length of the wire is bigger than the original length. Okay, so that is a plastic structure. Okay, so for an elastic structure, okay, which can be linear or non-linear. In this course, we are just dealing with the linear. Okay, so an elastic linear structure with constant temperature and rigid supports. Okay, now the constant temperature and rigid supports, this is actually implicitly hinting to something which is called conservative force. What is a conservative force? Conservative force means that if you have a certain point where you apply the load, okay, and this point you bring it to another position, okay, you will have to put some energy into it, isn't it? If you have a certain point, imagine I've got a ball, okay, and that ball I want to raise it to certain height. Okay, so I have to put some energy into it, isn't it, to bring it to the top, isn't it? So that energy obviously means, how do I pump that energy in that ball? Applying force, because you have to lift it and then you have to take it to a certain height. So that energy which is going in the ball, okay, that energy is then stored in that ball. Agreed? The conservative field means that no matter what path I take, okay, to take that particular point from one position, say A, to a position B, no matter what path I take, the energy which I put into it and the energy which comes out, that is the same. Okay? In other words, you might, the part is independent of the energy which is being given to it. Okay? And the common example of this is gravity. Isn't it? Gravity everywhere is the same. So if you bring this pen straight, you drop it down straight to the ground, or you bring it through a certain channel and then bring it down to the ground, the energy which is lost, that is the same. It's path independent. That is a conservative field. The field is conservative and the force is conservative force. Do you understand my point? So it's regardless whatever path you take, okay, from bringing a point from one position to another position, regardless, the energy in the system stays the same. Okay? In other words, the energy which you put into it, and obviously that energy will be coming out later, so that energy which you put into it, that stays the same. You understand my point?
Yes,
so that is your, so that is called the conservative field and conservative force. Now, in the case of structures, how does that work? Like for example, I have got a beam. Okay, I have got a beam which is subject to some loading P. This loading, under this loading it will deflect. Okay, under this loading the beam will deflect. Now, if I apply a certain load, it will come to this position. Now, if I take this load and put it, start applying it in portions, okay? So initially, what happens? I mean, a proportion of it I apply, it will come here. Another proportion I apply, come here. Another proportion, and ultimately, at load P, I would have this deflection. Okay? So this is also a conservative field. In other words, all these portions, if the energy which goes in all these portions is equal to the energy which this beam will consume while coming to this blue pole, taking the blue deflection. You understand my point? So all these deflected curves, they will sum up into giving you the final deflected curve, which is the blue one. Do you understand my point? How this conservative system works in your structures?
Yes, sir.
If this was not true, then you wouldn't be able to add all of them. That's why you are applying the principle of superposition also. Principle of superposition means that if you have a load P applied, so I can also divide it into two structures of the same type and apply this P by 2 and P by 2. Okay, so half of it and half of it, the total. So whatever internal energy this will have, okay, I mean whatever internal energy the load P applied on a simply supported beam would have, that is equal to the sum of a portion which is 50% of the load applied and then 50% applied later. So in one go you apply 50% and then another 50% you apply later and you get the same curve. So that is, so this is called principle of superposition. So my point is that if you have an elastic structure with a constant temperature and rigid supports, okay, in that your internal energy, if you take partial differentiation of the internal energy, the energy which goes in the system, okay, this energy can be in the form of extension or this energy can be in the form of a bending moment. Okay, internal energy can be extension, isn't it? Like in truss structure, truss is getting extended when you apply an axial load on it. So that is the so that is the internal energy in truss. In case of beam, when you apply a load on it, you have moments in the beam. Okay, that moment is actually internal force. Okay, so the internal energy you take a partial differentiation with respect to deflection at a particular point, you get the load which is applied at that point. So in other words, if I have a beam where many loads are applied, okay, and under these loads I have got some deflections. So imagine this is P1, P2 and so on so forth, Pn, and this is delta 1, delta 2 and so on so forth, delta n. Okay, all these deflections which are under the applied load, if I take the internal energy of the system, it will, how do you find out the internal energy? That will come later. How can we find the internal energy of a beam? That will come later. But if you take the internal energy of this system, okay, and you partially differentiate that with respect to a certain deflection, say delta 2, okay, thirdly delta 2. So you will get the load P2. You will get the load P2 which is responsible for causing your deflection delta 2. This is called Castigliano's first theorem. Now how is this derived? That we will discuss. Any questions so far? The energy, the internal energy. Look, what is internal energy? Internal energy is the energy which is consumed by the system. Like for example, if I have got a bar, okay, and I apply load P on it, I've got a bar and I apply load P on it, okay, so the bar extends. The bar will come over here, okay, after extension. So the extension I call delta, okay, so if I draw P delta curve for this delta will come out to be a straight line. Why? Because I told you that we are dealing with linear elastic structure. So this will be a straight line. Internal energy is nothing else but the area under this curve. This is your internal energy. Okay? So, and this internal energy is equal to, what do you think it should be equal to? Half times P delta. That is the area under this curve. That is your internal energy. Okay? So, you have internal energy which is half times P delta. Now, what I am saying is that if you differentiate this internal energy, similarly in the case of beam, now this is for axial, okay, and we know that delta is equal to what is delta normally equal to? Delta is equal to PL over AE. So U energy is half P square L over AE. This is your energy, internal energy equation for the axially loaded bar. Okay? Sorry?
Is this called strain energy?
Strain energy, yes. This is also called strain energy, okay, which is the internal energy. So strain energy, why do we call it strain energy? Because the fibers inside the structure, they get strained. So we call it strain energy or energy. Okay, now in the case, what happens in the case of a beam? If we have a beam which is subject to some load P, yes, and this beam, imagine this beam deflects. So when it deflects, if we draw tangents between 2 points, let this be theta. Okay, and there is a force over here which is moment M. Okay, on this is everything okay? So we have a beam which is subjected to some loading. Okay, excuse me sir, is there a problem? Sir, what's the problem? What are we saying over here? No, what are we saying over here? What is going on over here? Can you make me understand? Dekhiye, I've told you, really frankly speaking, I'm not restrictive about your attendances. Okay, so the guys who don't want to be here, please, like I can mark all of you present, no problem. Okay, but what I need is concentration, because you know in the beginning also I'm just losing the string of my arguments. Okay, and that distracts you. So please, I request you that don't do this. This is the second time I'm saying we have got only 1 hour class, and in this also we spend 5-10 minutes just on, telling off each other. That's not good. So what I'm saying is that we have a beam, and this beam has got internal moment. Yeah, beam has got internal moments. These internal moments are actually responsible for causing internal energy. Okay, they are the main parameters which cause internal energy. Now, this internal moment M, okay, it makes angle theta. Okay, so in other words, this internal moment M, it caused the tangent of this elastic curve to deform. Okay, so we can write analogous to this one, M and theta, and that is also a straight line. Okay, so U internal is equal to half M theta. Agreed?
Yes, sir.
And this thing, now, what is our theta? This theta, yes, this theta from our first theorem of area moment. Remember, if we have a curvature like this, and we take a tangent at this point and tangent at this point, these two tangents meet at a certain point, so we call this d theta, and these two tangents are also d theta based on trigonometry, yeah, and we said that this is actually rho, this is the radius of a curvature, so we can write ds is equal to rho d theta. Can we write that? Yeah, and 1 by rho is equal to d theta by ds. We can write that. Yes. This 1 by rho is also equal to m over ei. I think so. This should be very clear to you now. 1 over ei. So d theta is equal to m over ei ds, which is approximately equal to m over ei dx. X being, if we are taking, if this is x, this might be dx. Okay, so this small portion is dx. So what I'm saying is that this curve and the straight line, they are the same length because we are dealing with small displacement. So d theta, do you understand my point? So in other words, ue is equal to integral half and d theta is, so this is m square dx over ei, and that is the surface. Okay, this is the internal energy of a beam. Okay, so these two, we will be dealing with these two equations. So what we are saying is, so my point is that if you have a straight beam, yeah, which is subject to some loading, the internal energy you can find using this equation for the beam. Okay, and this internal energy is for the whole beam. It's not for one load. It's for all the beam, which means support condition and the applied load, everything. Okay, this internal energy, if you differentiate that with respect to a deflection at a certain point, imagine I take any deflection underneath any load. Okay, that will give me the magnitude of the load which is applied. Okay, that's what this equation is saying. Have I answered your question? Yes, so that's what I'll derive it. Okay, how this is derived? Very straightforward. Shall I rub this off? Okay, so how can we derive this equation? Now imagine we have got a structure. This is a structure. I've just drawn a structure. This can be a truss structure. This can be a frame structure. This can be a beam structure. Any general structure which is supported. So this is the structure and it is supported over here. Okay, so these are the supports, and we have got this structure. Black area is that instant of the structure or that position of the structure when no load is applied. In other words, when it's the initial configuration of the structure. Okay, when you haven't applied any load. Do you understand my point? Like for example, I've got this bar and initially before application of the load, it is like this. Is that okay? Okay. So what I'm saying is that you have a structure which is in initial configuration is shown in black, okay, and that is supported. What I do is I apply certain loads on it, okay. So imagine I apply certain loads. So we have a load like this, load like this. we have got a bunch of loads which are applied on this structure. Okay, and when we apply the loads, it will deform, won't it? So after deformation, it takes the position blue. Okay, that's the configuration of the structure after deformation. Okay, so now, what do you think, what is our external work? Half P delta. Summation, isn't it?
Yes.
Summation half Pi delta I. That is the external force. Okay? So after applying this force, okay, on the structure, it deforms. Now, once it deforms, then what we do is we apply additional deflection under particular load. Imagine under this P3, I apply additional deflection. Okay? In other words, I deform it further. Imagine I have got a rubber band in my hand and I deform it. Okay? Keeping all the other positions the same. All the load positions. So in other words, so what is happening is the red one is showing that you have a structure under the application of the, what do? I apply a certain deflection, a very small deflection under the load P3. What I am saying is that I've got a beam, yeah, and this beam has got many loads, okay, and this will give me a deflected profile like this, okay. Now what I do is, okay, so essentially your loads are applied on this red profile, agree? After application of the load. Now, after that, I slightly deflect this point in such a way that the position of it at other location stays the same. That's what I'm doing. Do you understand my point? What I'm doing? I'm just slightly deflecting up. This is one load. Just out of this bunch of loads, I've got this one load. Under this load, I just apply some additional, a very infinitesimal deflection. Okay? Under this load, a very small deflection in such a way that the deflection under the other load stays the same. It is very small and it's applied under one load of interest in such a way that the deflection under the other load stays the same. That is what is shown over here in red and I've shown in this diagram in green. Do you understand my logic?
So how have you achieved it? I'm increasing the load P3.
No.
And how?
Yes. You have slightly applied the deflection, increase the deflection. So obviously your load will slightly increase. But this is very small. We are talking about extremely small, infinitesimal. Okay, very infinitesimal increment in this load, but that is so small that it doesn't affect the deflections of the other. Okay, so what we say is, so what would be the external work done in that case? Okay, so let's see. This is our pi delta I curve, okay, which is, imagine which is straight, okay. This is delta I, okay, for a particular magnitude of pi, say pi, I've got delta I, okay, or this can be P3, delta 3, initially, okay, when I get this blue configuration. Now I slightly increase it to d delta I. Okay, I go slightly ahead. Delta I plus d delta I. Okay, so what do I get? I get this increase. Okay, so the change in work done, which is dWe, the external work, equal to area under this curve I told you. Yes, so that is area of this one and area of this one, agreed? Area of 1 and area of 2. Area 1 is how much? D delta I. And area 2 is half dpi into d delta I. Now this becomes too small. So d delta I on its own is small, and multiplying that with another small makes this almost equal to 0. So what we get is, and the external work must be equal to internal strain energy, isn't it? External work which you are the energy which you are pumping into your system is equal to internal energy. Agreed? So dUi is equal to pi d delta I, and we can write 30 ui divided by 30 delta I is equal to pi. Okay, so I'll repeat what I've done. I'm saying that I've got one system which was in its original configuration. Okay, no load applied, which is shown by this black one. I apply the load and I apply a bunch of loads. Okay, and I get the blue configuration of the system. Okay. Now, so, and that blue configuration, I come over here in my P delta curve. Now, from this point onward, I slightly incrementally increase the deflection under the any load of interest, which I call Pi, P3, or whatever you want to call it. Okay, I slightly increase that, so I go differentially ahead. That is a trapezium. That's trapezium which I get. So that incremental increase in the work done would be equal to the incremental increase in strain energy, and that is equal to, in turn, this area of this trapezoid, which is d delta I pi and half pi d delta I. So we get so we are not we are ignoring the higher order terms. The higher order terms, so that comes out to be 0, and we get dui is equal to pi d delta I. Okay, you just take it to the other side and you get the same. Equation. Any question about this one? Sorry? Because these are two. You have got a very small number, 0.00006 something. Okay? You multiply that with 0.00007. So what will you get? Almost 0 in here. So it's already small, and then you multiply it with another small value. So you get 0. Yes.
What is the purpose of providing the extra deformation?
What is the purpose of providing the extra deformation? Look, this extra deformation we have provided to prove this theorem that if you have the internal energy of a system, you have got an equation which gives you the internal energy. Like for example, don't think about this as a beam. Think about it as a big finite structure like this room. Okay? And this room is subject to many loads, isn't it? If you manage to find out the internal energy of this room, okay, what will happen? You can use that internal energy equation to find out load at any position on this room if you don't know it. Do you understand my point? Okay, so if there is any unknown load, if I have got some mechanism to find out the internal energy of this room, okay, derive its equation, then, and I don't know how much load, how much earthquake was this room subjected to, okay? So, and I say that, okay, there is a mass over here. Obviously, earthquake load is a function of mass, and the mass, maximum mass, the center of mass is somewhere in this region, okay? In this region, there is a center of mass. So, at that particular point, I can differentiate that with respect to differentiation, to deflection, and I can find the unknown load which is causing that deflection. So that's why in order to derive this equation, we actually were using this, I know a bit of convoluted concept, okay, that we have a structure, apply the load, and then underneath a particular load which you don't know or whose rate of increase you don't know, you just slightly apply additional deflection underneath that, and what will happen? You will have the final, you can find that unknown load. Okay, so that is the first thing. I can't redraw. This is, I just need 5 more minutes because the theorem 2 is just similar to this one. So I don't want to redo this as a thing.
He has lived his life, and the most remarkable life. तेरी लाइफ बढ़ जानी है गुलामी की।
Thank you very much. You are doing a good job. You know, I've hired him actually. I pay him. Okay, these are my salary. That's why he defends me. Yeah?
Maybe someone will work out.
Okay, so theorem 2 is more or less similar to theorem 1. Okay, theorem 2 states that if we have a linear elastic structure, okay, with constant temperature and rigid support, then if you have an internal energy equation, you differentiate that with respect to the applied load, you get the deflection. And this theorem we will be using in deriving our deflections for different structures. Okay, how is this derived? Imagine we have again the structure. Black configuration is again structure which is subject to different sets of loads. Okay, a bunch of loads. Yeah, and then once you apply, I am saying that black configuration is when no load is applied. After this, you apply bunch of loads on the structure, and it takes the blue deformed shape. Now, what is we know that internal energy is equal to external work. That is well known, yes, and internal energy is summation of R can I write that? Internal energy is half Pm delta M. Okay, so in other words, that I told you that if we have a P delta curve, all the loads, you keep on applying that. Okay, you keep on applying your load. You apply all the loads onto the structure. What will happen? If you are in the linear elastic range, then the internal energy is area under the curve, which is R load into delta. Okay, so that is our internal energy. Now, what happens is, imagine I say that okay, so if I apply in theorem 1, I applied a deflection. Over here, I apply some load, additional load. So this is P3. I add okay, a very small increment of this load. Okay, so I superimpose an additional load or increase the magnitude incrementally by one increment, by one very small increment. I increase the magnitude of this P3 by one very small increment. So what will happen? I will have obviously change in internal energy. Yeah, and that change in internal energy is equal to, so initially we had ui, and then we will get dui, which is equal to using the chain rule. Can we write that this is rate of change of u with respect to p times dp? Because this dp will cancel out with this one and we will get again the dy. Can I write that using chain rule? Agreed? Okay, this we have done. You guys have done, yeah? So that is our internal energy. Now we say that the system is conservative. As I said, conservative system means that if you have certain set of load, okay, if you apply that initially or in the end, the deformation it produces will stay the same. In other words, if I have just dp3 applied initially on the structure, I started off by saying that we apply first the bunch of load, okay, and then after that we apply dp3 on top of it, isn't it? That's what I said. But I'm saying that now, if I say that I've got dp3 only applied on the structure, and then after that I apply all the bunch of the load, the energy within the system will stay the same. Do you understand my point?
Yes.
So that will be, so again, ui so what we have is sorry, P1, P2, P3, these are loads which are applied on structure.
These are constant, like constant values of constant load applied on structure.
Yes, like you know your structure has got 4 kip load, 5 kip load, 10 kip load, that sort of load.
So how can we differentiate some equation with respect to constant values, sir? Like we are differentiating energy equation with respect to del Pi, sir.
Del Pi.
Yes, sir. P is constant here, so how can we differentiate?
No, P can be of any value. What do you mean constant? P can be any value.
But sir, in our case, if we are finding
If
value
you are
of
saying
any-
that if
something
we have P
like-
applied, but that we are talking about a general case. A general case. Okay? In a general case, we have these loads, okay? They are applied on a structure, okay? These loads can have any value.
Are they same?
No, they can be different. The load is variable in that sense. Okay, why? Because the load can have any value from 0 to anything, okay, and it can have, and there can be any set of values. So the number of loads is also different, because we want to develop a general equation. We don't want to say that, okay, I want to have just one particular beam which is this much length long and which is subjected to 5 kilonewton load, and that's it. No, I want to have a general equation. That's why in that sense my P is variable. My P is variable.
But if we want to find a deflection about some fixed loads, if like we are going to find deflection.
But this is general. Any point I want to find out load. I don't know. I mean, like, this can be any point. This load can be anywhere.
Any point,
Yeah.
So that is variable. Do you understand my point? It's not a fixed constant load. I'm not saying that P1 is going to be only 10 kilonewton, that's it. So load value can vary, okay, and the number of loads can vary. This is, you pick any load. That's why I say PM or PI, any load. Okay, so this is actually a variable. So what I'm saying is over here that initially so what I'm saying is that initially, say we have the load dPi applied on the structure, that will produce d delta I, this deflection on structure, okay, and then after that we apply our loads, other loads, okay, so that produce delta I and you can say Pi or delta M, PM, whatever you want to call it. But the other loads is applied later. So, what is this? Half. So, area under the curve we have to find. So, we have this time 3 areas, isn't it? We have got 3 areas. So, this is half. Okay, so what do we have? We have this area, we have got this area, we have got this area which is dPi times delta I, and we have got this area which is dPi plus all the other load. Okay, so therefore summation of half PM delta M. Agree? So this one. So we know Ui is equal to this one. So this one can cancel out with this one. Agreed? This one is again small, cancel out. And we get Ui is equal to okay, why am I saying that this is going to be a partial derivative? The reason is, partial is for many, if you have variables, if you have got many variables. Like differential, one differential is if you have got one variable, like x. Okay? Partial is if you have got many variables, x, y, z, l, and so on and so forth. So, the reason that I am partially differentiating it with respect to p is p can be anything. There are lots of p. Okay, so that's why it becomes partial. Yes.
Very last term to cancel you.
Yes, sir.
This
No,
one,
sir. The rightmost.
because I said that initially internal energy was equal to half pm. That time this was the initial one, isn't it?
Yes, sir. What is okay.
So therefore ui and this one got cancelled. We derived it over here initially. When we apply the load and it deforms internal energy, external energy, and it's equal to this. Agreed? Any question about it?
No, sir.
Okay?
Thank you, sir.